Now let's discuss Thevenin's theorem, which is another important theorem for network analysis. The Thevenin's theorem simplifies the complex linear electrical circuits into equivalent circuit consisting of a single voltage source VTH in series with a single resistance RTH across a specified load. This simplifies the calculations of voltage and current through a load resistor, particularly when the value of changes repeatedly. Okay, let's see a very complex circuit, so which means we have power supply and a lot of resistors are there. So when we want to analyze this one, each loop, this is very difficult to analyze. Therefore, we have a theorem called the Thevenin's theorem, which will help us to do this. So what we do is, instead of this complex network, we can replace with a power supply, which is VTH, which is Thevenin's voltage, and another series resistor RTH will be series with this one. Okay, this is a part we can connect the load, so that the connections, this simplifies the complex network into a very simple a voltage and resistor series circuit. Okay, let's do one exercise on LTspice. So I made a circuit. It's not very complex, but we can analyze this using this LTspice. Here we have a power supply of 12 volt, and I put all the resistors 1K, R1, R2, R4 and RL. Load resistance is also there where we are putting the load. Okay, for simplicity I put all resistors to 1K. Then what you do is we have to do the Thevenin's analysis. So the first role is to find the Thevenin's voltage VTH and the resistor RTH. For that, what we are doing is we have to first find VTH. For VTH, what you are doing is you replace your RTH from here, which means that you have two open-ended points, which is I can make some comments on this one. I can put an A. Okay, this NTA. So this is an option to put comments. So this text portion is that I can put open it and make whatever comments in the schematics. Okay, there are 2 points A and B. What you do is if I remove RL, this will be open. This is open-ended ends. So what you do is then I can find the Thevenin's voltage across this. So this is open. The voltage across will not be counted. Therefore, we can use a potential divider analysis to find VTH. That is, your total voltage is 12 volt into voltage across R2 is 12 into R2 divided by R1 plus R2. That means 12 divided by 12 into 1 divided by 1 plus 1 is equal to 2K. Therefore, you get a 12 by 2 is equal to 6 volt. Therefore, the Thevenin's voltage you can calculate as 6 volt. Then the next thing is RTH. So for that RTH, what you do is you have to replace all the voltage sources and short circuit it. So there should not be voltage. You can directly short circuit this voltage to this one and find and also remove the RL. Then you find the load resistance from this end. Okay, then if I remove this one voltage, what will happen? This become parallel. So 1K will parallel with 1K. Then plus one more resistor is series with that one. That is plus 1K. Okay, so if you add this one, what will happen? 1K plus 1K, parallel is 1K, you get 0.5K plus 1K. That means you will get a Thevenin's resistance as 1.5K. So the required calculations are done. So for if I can replace with this circuit with a power supply of 6 volt, that is on my VTH, and a series resistor of RTH 1.5K, this will actually work similar as this complex network. So that's the essence of this Thevenin's theorem. Let's check we are getting the same current and voltage across this load resistor. Okay, so for that I have done a transient response. You can give a 0.1 second for this transient response. Let's do the simulations to see what is a current and voltage across this terminals. Okay, I will run the simulation. So first I check the voltage across here. This is 2.4 volt, and here also this is 2.4 volt. Okay, then I want to find the current. So if I measure the current, it is showing as minus 2.4 milliampere here. So again, if I measure here, that's also same, which is also 2.4 milliampere. So that's why we have varied that. If I can, this very complex network also I can do the same thing and check that the complex network can be replaced with a simple voltage source and a series resistor.